All right, cool. So it's time for our next talk. Maddie Stone is with the Android security team. She was telling me earlier that she actually gave her first ever conference talk here at RECON 3 years ago, which is really awesome, and we're very glad to have her back.
Thanks. So hi, I hope you're here for the Path to the Payload Android edition, because that's the only thing I'm planning to talk about. And we'll maybe get some slides. Can't you see the payload and the path to it here? Well, there we go. So, hi, I'm Maddie Stone. I am a reverse engineer and am the tech lead for Android security research and operations in the off-market and pre-installed spaces. So basically everything that's not Google Play. So I've been reversing about 6 years and joined Google about 18 months ago. So prior to that, was doing the offensive work in hardware and firmware. So Android's a little different. Our target of analysis today is this app. It's a bit.ly link that goes to the virus total. Can I? Too much hair? That's not gonna work. Friend. Just a little calisthenics to get warmed up. But our target of analysis today is this application, which is a member of what I call the Nicro SDK botnet, which is exclusively off-market, so in the side-loaded distribution mechanisms of Android. And so the purpose of this talk today, no story, no impact numbers, no threat intel. We are literally just walking through all of the different steps that it takes and the status analysis required to even get to the payload. So I have 55 slides to go through in these next 30 minutes, so prepare for a lot of code and what it takes to get to the payload. So first, here's our overview. There's 4 total stages. The majority of this talk is focused on stage 1 and stage 2, because that is where all of the mechanisms that require the setup, the anti-analysis checks, the deobfuscation occur prior to the payloads coming. We will unpack stage 3, but stage 3's purpose is to set up the payload environment, and today's not about the payload, so that won't be covered. So first, we have our APK. We see it whether we're in virus or malware analysis environments, you're downloading it from a website, and that's stage 1. So the first thing they do to sort of throw you off the path of analyzing this application is that they have defined an application subclass where the majority of all of this occurs and begins. And what's interesting about an application subclass in Android is if it is defined, that is run prior to any receivers, activities, or services within your application. So yes, they have defined some activities, but those are benign, and they're not actually executed because this runs before them. So this is all the code that exists in the application subclass for this application. And there's 2 different methods in here. We have attach-based context and onCreate. Attach-based context is always run first, and then onCreate is run. And one of the things first is that all of our strings are obviously obfuscated, and we'll come back to that. The next thing to note is that these 2 methods, they look exactly the same, have the exact same method call in them, only the difference is an argument. So we need to remember that the one in attach-based context is run first with its argument, and then we'll come and run onCreate, again, running that exact same method, but with a different argument. So when we open up that method, that was called heading, this family for each different applications, they go ahead and dynamically generate new method, class names, etc. And each of those are just random English words. So in this case, we have heading, and the first call it makes is it does an if clause, and it is looking to check out its anti-analysis. There's 3 first checks, and it's in this class that's called com.inasmuch.trample.fly, because just look it up in an English dictionary, and the method is offer. So the very first checks they do are first, they're going to check if there's a default Bluetooth adapter on the device it's running, because a lot of emulators nowadays and dynamic analysis environments do not set up a Bluetooth adapter. Then they're going to look for a sensor as well, or I'm sorry, the sensor on it, which also a lot of emulators do not include, as well as sandboxes and things like that. The last thing they do is they're going to cat out proc.cpu info. CPU info, just like on your Linux computer, says which chip you're running on. And so if you are running on an Intel chip or AMD, which is what most large-scale automatic or dynamic analysis pipelines will run on for all of their emulators, they will also exit at this stage. But we've made it through that. So first things, this is what the code looks like to check for the Bluetooth adapter. So it's super obfuscated. All of the API calls they do are completely through reflection. But we're going to work through it, because it's just peeling back the onion. It's not that scary once you go through line by line. So when we come back to the heading class, again, we have all of our obfuscated strings and reflection. We can easily notice that all of the obfuscated strings are passed to the exact same method, which is that really obvious signal that that is our deobfuscation method. So when we take a look at component, which in this case is the deobfuscation method, this is our code, and it's pretty straightforward, not something super advanced. We have a hash code that we're XORing with after base64 decoding. But what's nice is that this is Java versus if they had written this in native code. So one of the nice things about when they choose to write their code in Java is you can copy and paste it generally from the decompiler. If you have a decent decompiler, just sort of fix up some things the compiler doesn't like, and then run it statically over all your strings. So that's exactly what I did. Within a few minutes, I then had all of the unobfuscated strings to continue analysis. So once we get through that first anti-analysis check, the next thing that heading method does is to unpack and load stage 2. So this occurs in com.convenience.amplify faithful chairman, and it's first going to construct a destination path. And one of the things that this family does is that they don't use the same path for every sample. So they're going to use certain characteristics of the device to create each of the paths, so it's not quite as easy to signature. So in this case, for this, the stage 2 path, where they're going to write the unpack stage 2 is cache / they're going to get a hash code of the string of the device manufacturer from the build.manufacturer field, plus the current process name, and get the hash code of that / and then they do the same thing, except for this time on the device model, again from build.model, and the process name, and then .jar. And so the source of what they are unpacking is actually in the assets file. And in this case, it comes from one of those deobfuscated strings that we just did, and its name is horsepower. Again, just random English words. We then unpack it, we write it to the destination path, and then we load one of the classes from our unpacked jar and begin executing. And so in more detail, this is what it looks like to unpack it. So our packed file has a very short, simple header. The very first byte of the header is the key length. Then the key follows after that for that number of lengths. The rest of the file is then the packed data. And so here on the left-hand side, you see that the unpacking algorithm looks kind of complex. There's a lot going on, a lot of different variables the decompiler has found. But when you take a look at what actually matters in there, it is simply reading each byte of the packed data, XORing it with the key, then XORing it with FF in order to XOR it, yeah. And then lastly, once it has that result of the XOR, it switches the two nibbles. So the high nibble now becomes the low nibble, and the low nibble becomes the high. And that is written back now to the destination path. And so in this case, I did not just use Java, because one of the tools that helps when you're doing static analysis to get through this much quicker is if you have a framework of a Python file that can read a byte, you just paste in the algorithm that you need to do, and then it writes it back out to a file. So if you have that framework in, then this is literally 2 lines of code that I basically wrote into that file and then used the Python script to unpack stage 2. So then we have our stage 2 jar. Right here we said after it was unpacked, we then used Dex class loader to load the class com.sdk.entry.sdk entry into our current process. And remember when I said that the heading method, the one that we have just been looking at, was called twice in that application-based subclass. So the first time it is called with the load attach context argument, and the second time it's with startLoad. So we are now going to, we now are calling into startLoad with the load attach context argument, because that is what we passed in. That is the point of that method that is called twice in the application subclass. So the very first thing that now here in our stage 2 unpack jar we're gonna do is we need to decrypt the configuration file. So the configuration file name came from stage 1. It was one of those obfuscated strings, and in this case it's assets/cabin. We're then within this method going to have to determine where is stage 2 running. So the key thing about the Nitro botnet is that everything is highly modularized and abstract. It's a well-engineered piece of code, which is why I was interested in talking about it. When I opened it up and started working through it, I was like, oh, this is interesting. This is good. So one of the things they do is they know that as a standalone jar, once it's unpacked, it could be running in a lot of different contexts. You as an analyst could write it up and decide that it is going to run within your app and things like that. So they actually go through and check their personal class loader for their current context and see if it is, who is the parent of it and whether it is running as a plugin of another process or within the stage 1 application. The next thing it does is it then passes and begins running whatever function is at the method name, that third argument. So the first time this is called, it's in load attach context, and that purpose is to unpack and load stage 3. We then return to stage 1 and go through the whole process again, this time from the application subclass call to heading. But this time, then we will pivot into stage 3. So that was the overview. Oops, I keep turning this off accidentally. Microphone problems. So, going back, how do we first decrypt our configuration file? We got it was asset/cabin. It is 15K. That is a very large configuration file and contributes to our knowledge that this is a highly modularized piece of code. So thankfully, this one was not customized, whereas all the other obfuscation mechanisms have been customized. They just use DES in the ECB mode, and they do have the ability to modify the key and update what key they want to use for encryption and decryption. But in this case, it failed back to the default key, which is the string CFGG_NFC. And once we decrypted this whole configuration file, it had 342 different configuration settings in it. And this is a screenshot of what they look like. So again, highly modularized. These are a lot of the different signals for the different types of plugins. What they call plugins, we call payloads. And it even allows them to spawn other processes, what those processes should be named, etc. So once we're here, we come now into step 3. We've checked in step 2 that we're running, that our class loader came from the initial application, and now we're in load attached context. So what we see here first is a class name that does not exist in package this stage 2 And what they're doing is unpacking stage 3. So we know that stage 3 that we're about to unpack probably has a class in it named this im application. So when we dig further into loaderPath, what we find is that they are first constructing the destination path for the Unpack Stage 3. And again, this time, they're using another custom destination construction. It's not the same one we saw for Stage 2, which adds another level of complexity to any signaturing or automatic detections. So what they're doing is they're going to write this to the cache directory, and the name of the file will be md5 of their current process name .apk. And so copy APK is where we're going to actually unpack and get this file from. Just has this call to a function write file, but this is where we can find out what is the pack stage 3 and where does it come from. So in this case, it is at assets/lib, and then they're actually reading from that unpacked configuration file, or decrypted configuration file that was encrypted with DES, to find out what the name of the file should be. And so this can be updated over servers, things like that. And so in this case, it is at lib. They did not choose an English word, but BFDRDON. So then we're going to actually unpack that and write it to the destination, which was the cache path. This was the whole thing. Sorry for the profanity. That's what they chose to use. But again, the Java is really nice in this regards, and it does make it smoother than if this had been written in native code, because once again, I copied from the decompiler, cleaned it up in a piece of code, and then just ran it over that file from the assets, and suddenly we had the stage 3 APK. So now that we have written this Unpack Stage 3 APK, we go ahead and use reflection to add that new path in the cache directory to our assets path so that then it can be class loaded. And that was the class that we didn't earlier see the name of. And then we go back to stage 1. So we haven't actually called into stage 3 yet. All we've done is load it into the current paths, or current processes set of classes that it can call to. So we just finished this very first call to heading in the attach base context. And in the Android application lifecycle, that means the next thing we do is call to onCreate. So we're going to go through the whole path again, but skip that very last method of load attach context, and this time instead we're down at bullet 5, where we will call startLoad, which will allow us to begin executing in the Unpack Stage 3 rather than just unpacking it. So this is where we see our calls into it. Again, just lots of reflection, and we're calling onCreate in stage 3. So stage 3 we're not going into. It is interesting and a lot of fun, but this is just getting to the payload, not analyzing the payloads. And the purpose of stage 3 is to set up a modular environment in order to allow many different types of payloads to run. When analyzing this payloads, it seems quite likely that they are paying, or people are paying them to distribute their payloads with different capabilities. It doesn't seem to come from the same authors, and thus they're able to support many different types of payloads by creating this modular environment. So they're able to set up and spawn different processes with different names, different configurations. If the phone is rooted, hook into other apps, change their functionality based on the Android runtime they're currently running on, and things like that. But in this case, since we can consider it the first run of the application, when they discover they currently don't have any payloads yet, they actually return back to stage 2, the jar that we were just looking at. And so once we return back to stage 2, we then go into the Sdklauncher class. And so what Sdklauncher is, it will again verify its execution path to make sure it is proceeding and has been called based on the expected state of execution. We're going to then check out make sure we have the permissions we need, and then we're going to load the plugins, again their word, which instead of payloads from the C2. So this was something I hadn't seen that often before, but makes a lot of sense when you take a look at it. So what they do to verify the execution path is they get the stack trace for their current thread that they're running on. And then they go through each returned StackTrace element in order to see what is the class name and what is the method name of that StackTrace element. And they verify that somewhere within the StackTrace is the onCreate method within com.wag.congratulations.lc. And the reason why they do this is, remember, onCreate is the second method called from that application subclass. So if you were trying to instrument this and you went into this class from attach-based context, then they would know that this has not proceeded correctly. So we've passed that check, we're moving on, we're executing as they believe it would in the wild. So the next thing they have to do is they just verify that they have the permissions expected. And so they just use the normal API call here, obviously through reflection again, and they want to make sure they have 3 different permissions. Write external storage, which is what allows you to write to the SD card or other external storage. And the reason why they need that is because they're downloading a lot of plugins and they need that space. And so that's where they write all the plugins to. Read phone state allows them to access IMSI and IMEI, and if you are going to do things like toll fraud as well as a lot of other types of fingerprinting, you generally use those types of fields and variables. And lastly, in order to do a lot of types of ad fraud payloads, you also usually want system alert windows or windows like that. So yeah. So then, this is a little bit different of a stage, but they had a lot of interesting techniques that are required to get to the payloads here. So, just a quick overview, these 2 communications are considered the command and control communications coming from the stage 2, that Unpack jar, because that is our framework that basically controls the whole piece of malware. So from stage 2, they interact with the command and control server in order to get the list of plugins, but prior to sending any of those HTTP requests, they do anti-analysis checks. But what sets them apart is they do not exit if they detect they're being analyzed. They send a modified request instead, which sends a still malicious payload, but not that malicious. So that was really interesting because when you take a look at it, and even myself when I was in our dynamic analysis environments, I was like, oh, okay, this is just, ad fraud or something like that. Still flag it, but move on, not realizing the extent of the sort of botnet capabilities. So the first anti-analysis checks begin with checking if the type of the build is an eng build. And so if you don't know Android, there are 3 types of builds you can have. Eng, which allows the most capabilities for use in an engineering environment, like it doesn't do verified boot, has a lot of tools, etc. User debug, and then a user build is what comes sort of if you buy the phone out of the box. So if they detect that they're running on an eng build, they don't do any other checks. They just send the HTTP request without any of the other properties they're going to look at. If they're not an eng build, they're going to gather a lot of other emulator and debugging properties, but they don't make the decision about how to run in the app. They send all of those properties up to the server, and the server will then decide what to deliver. So these are all the device property checks they do: row debuggable, row.secure, which are system properties. Secure is usually set when the device is rooted. A lot of malware authors currently will not run on rooted devices because it means it's much more likely to be caught, which is kind of counterintuitive sometimes. They're going to check if the flags on the application info have been set so that the application is debuggable, ADB. And one thing that makes a lot of sense when you think about it, looking back, but I hadn't seen before, is they also check to see if the app is currently running in a proxy. And so these are all of the checks they use to get that information. And then they move into emulator. Their word is simulator within the code checks. And so these can be grouped into 3 different categories of checks. So the first one is, again, they're just checking CPU info, making sure they're not on Intel or AMD. Next is, I'd never actually heard of BlueStacks before. So they are iterating through the file system to see if there's any one of, I think it's 18 different files related to BlueStacks. BlueStacks is an emulator that's actually meant for gaming rather than security analysis or things like that, or developing apps. So its main purpose is for running mobile games on desktop computers. And lastly, they look for a lot of hooking hinges, sandbox, and dynamic analysis tools. So first, they check if in the installed apps is exposed framework or Cdadian substrate, which are two hooking and instrumenting frameworks. They will then iterate through all of their processes maps to see if either ComSarc substrate or the exposed bridge jar have been mapped into the current process's memory, meaning it's likely it's being instrumented or hooked. And the last one is something that was pretty fun and interesting, is they purposefully throw an exception, get back the StackTrace, and then look through each of those, the StackTrace for these things. If any one of these are found, it's considered a fail. So first, they look to see if zygote is mentioned twice. Because normal zygote, spawns everything, is the base of the Android operating system, and so it would usually only be spawned once, but in this case they're seeing if it's been spawned twice. They look for a lot of exposed and substrate methods, as well as then finally looking to see if there are any methods from Cuckoo Sandbox or Droidbox Dynamic Analysis Engine. So once they've decided what they're going to do, then they have to send the C2 request. And so remember, if they detected that the build type is eng, they're just not going to include any of the properties that we just talked about for device properties or emulator detections in the request and just cut it off early, but still send it on. If they have detected, or if they were not on an eng build, they're going to send up all of those properties with just other names associated. So it's not like is being debugged or anything like that. And so obviously, if they've done this much work, all of their C2 requests were encrypted or obfuscated, rather. So what they did is they did not do the normal of here's a string, decrypt it, then pass that string to a writer, is they created subclasses of output stream and input stream that were doing the writes and the reads, and in those, in line with writing to the HTTP connections was where they were doing the encryption. It's a lot of code, so I did not include it because it would just be like font size 4, but what is nice again is the decompiler does a pretty good job, and it only took minor edits to the casting to get it to work, and then we are able to both write correctly obfuscated requests if you would like to send them to a milker to get, or use a milker to send them to the C2 in order to get the payload requests, as well as decrypt or deobfuscate all of the responses that you receive. And from there, we now have the payloads, and so that has been about 55 slides in 30 minutes, just in the weeds, just the code. And so a few takeaways is it's pretty entertaining and fun as a reverse engineer to see such complex engineering going into some of these pieces of malware. And despite the layers, though, of obfuscation and abstraction, and when you open up that initial app and you're like, what in the world is it doing? If you just take it one layer at a time, none of those things I talked about were super complex in and of their own right. So if you take it one step at a time, it gets pretty clear. And I also thought this was interesting because I might be a little language elite sometimes and definitely like the assembly and native code and always think it's better because Java, you just read it. But I think this was a cool example of how Java can be more complex and a fun challenge to reverse. But one of the nice things is it's not a fancy solution, and you don't need a fancy solution, is you can pretty easily deobfuscate and get past any sort of algorithms they use if it's in Java by just copying from the decompiler and into another file. And so even though they used 5 different obfuscation algorithms, none of them took a lot of time to do. And so with that, thank you. Are there any questions?
Well, thank you for your presentation. You were saying that the malware was checking proc maps, and they were checking if you were having like expose or substrate. So my question is, have you seen any malware trying to detect, for example, Frida? Because I think nowadays many people they are using Frida. It's a state-of-the-art hooking framework, and you know.
Yeah, newer versions and variants of this have started to use Frida when we started also flagging them and stuff, as well as a couple other families have evolved in about the last 6 months was when we first started seeing it, started to be checked for in anti-analysis checks.
Okay. Well, thank you.
First of all, nicely done. That was a great presentation. I imagine that the reversing process wasn't nearly so straightforward as the slides that you just put out. What were the major hurdles that kind of stopped you up and interfered with the process, and what made them so difficult?
Yeah, so actually in stage 2 and stage 3, everything is largely abstract. So they're using a lot of interfaces, which decompilers don't do well with interfaces and superclasses and subclasses. So you can't easily see the cross-references between them because they're saying, this is the implementation, and there's like 20. And you're trying to track back multiple layers to find out which implementation is being used in this one case for this object. So I think that's the biggest hurdle. And so it actually took me a while to realize that stage 3 was setting up all of these environments for payloads and wasn't actually going to get me to the payloads, and that was actually back in stage 2 because I got caught in those layers of abstraction.
Hey, what was the most challenging anti-analysis to bypass?
So I think that's the thing is I default to static analysis largely. So hence this talk was all static analysis. And so I don't really think of it in those terms that much, but I think the hardest thing to bypass that I talked about would, I don't know. I think it's more of the series of them, is that you think you get past the first set of the 3 simple checks for sensors and adapters, and then you think you're good to go, you set up your environment and realize it's not actually going to run. Oh, the hardest one was actually realizing that they were delivering fake payloads to me, knowing that it was being analyzed, and I didn't realize that they just weren't sending the full response, so I had to go hunting for that. Gonna get your steps in.
Sorry, that's kind of loud. I was just wondering what the most popular monetization schemes you've seen for these botnets.
It depends on the region of the world. So in Southeast Asia, it's primarily mobile billing fraud, which is sending premium SMSs, signing up for WAP billing, and things like that. Hostile downloader networks are pretty big, and I think ad fraud, I don't know numbers, but I would guess just based on how everything is going, ad fraud in terms of false clicks or showing invisible ads is probably the biggest monetization.
Hi, great talk. What made you decide to continue pursuing, like understand that this is not a real payload and there is another one behind it?
The amount of code and abstraction, it just sort of raised a red flag that the payload they sent me was not obfuscated, wasn't using reflection, was pretty straightforward and like very clearly on the first class showed me what it was doing. And that first payload was just doing click fraud, but not very often. And so it just sort of, the intuition said there was probably something more, and I went back a couple months later and took another look. Thank y'all.